Hello friends, today we are going to talk about the ideal gas. Okay, so the ideal gas is basically also called the general gas equation, and this is the equation of a state of a hypothetical ideal gas, and it also states the product of pressure and the volume of 1 gram of molecule of an ideal gas that is equal to the product of absolute temperature of the gas and universal gas constant. Okay, and R for most part gases all follow the equation, that is PV is equal to nRT, and where V is the volume in liters, N is number of moles, and T is the temperature in Kelvin, and R is a constant which is equal to 0.08206 liters atmosphere per mole Kelvin. Okay, and according to the ideal gas law, if the temperature and amount of gas are held constant, an increase in volume will cause a decrease in pressure and vice versa. This is because the molecules have more or less space to move. That will affect the frequency of collisions with contained walls, which defines the pressure. Now let us come to the the major category of an ideal gas problem is categorized into four. So first one is the ideal gas equation problems, and we have the combined gas equation problems, and we have the gas stoichiometry problems, and then we have the Dalton's law of partial pressure problems. Now the first one is the algebraic approach to the solving of such kind of problems. So first of all, we have, what is given in the problem, we have to write down its values. Okay, and then we will assign the various variables to each. Write the exact equation that we are going to apply, solve for the variable of the unknown. Now we will plug in the values that is given, including their units, cancel units, and if necessary do unit conversions to get the units to cancel, and then we will do the calculations and report our answer with the current significant figures and unit. This is very important. Now a unit check, if our units cancel to yield the correct unit of units, so we must know that we have to use the correct equation and they'll do the algebra correctly and do all the necessary unit conversions. Then this is my ideal gas equation, where P is directly proportional to the number of moles, temperature, and inversely proportional to the volume if N and T are constant. So this is P in the pressure will be directly proportional to N into T upon V, and P is equal to A into constant into N into T upon V, where, or we can say that PV is equal to N into A constant and T. So now PV is equal to nRT, and R we all know that is equal to 0.082058, or you can say 0.08206 liters atmosphere per Kelvin into the moles, or in terms of other units it's 8.3145 liters per kilo into kilopascal upon K into moles. Now expanded ideal gas equation, okay, we can say that PV is equal to nRT, and R has two units, we already saw that, and N is equal to moles. So moles is nothing but whatever mass is given. Suppose we have nitrogen gas, so in that case if it is 2 grams, the mass of the gas, so it would be 2 upon the molar mass of the nitrogen gas, which is equal to G upon M, given weight upon the molecular weight of the gas. Now PV is, if we replace this, so it will be G upon M into RT. So G is the mass and M is the molar mass of the entity of the gas. Now ideal gas equation problems, the usual tip of that we have to use the ideal gas equation to answer a question is that we have three properties of a sample of a gas, and we are told to calculate the fourth one. So three is known and the fourth one is unknown. A more general tip off is that only one gas is mentioned, so there is not chemical reaction mentioned and there are no changing properties. Now the ideal gas equation problem step 1 is assign the variables to the values given, and the value that is unknown. Use P for pressure, V for volume, N for moles, and T for temperature, G for mass, and M for the molar mass. Now step 2, if another kind of this is another type of, so write the appropriate form of the ideal gas equation. If the number of particles is given or desired in moles, use the most common form of the ideal gas equation, which is equal to PV is equal to nRT. R, we all saw this. If mass or molar mass is given or desired, use the expanded form for the ideal gas equation. So instead of N, you have to put G upon M. Now, third type of problem would be you have to rearrange the equation to isolate the unknown. I mean to separate the unknown or segregate. Plug in the known values including the units. Be sure to use Kelvin, temperature, not the degree C, and make any necessary unit conversion and cancel your units. Step 6 would be calculate your answer and report it to the correct significant figures and with the correct unit. Now, for example, most incandescent light bulbs contain argon, which is an inert gas, does a better job of slowing the evaporation of the tungsten filament in the light bulb because it's inert. Because of its higher cost, however, krypton is only used when longer life is expected. How many moles of krypton gas must be added to the 175 ml of the light bulb to yield a gas pressure? So we know here what we know. We know the volume of the gas, we know the pressure and the temperature. So we are told to find the moles, any N. Okay. Now we will use this equation, and N we all know that is equal to PV upon RT. So pressure we know, and volume, make sure we know the correct form. So suppose this is in kilopascal, so we have to use this one. If we go back, you can see here R has two forms, so we would be using this form. And also, okay, so this is a kind of conversions, 1 liter upon 10 to the power 3 ml, because here it is in milliliters, so we have converted this to liters because here all the forms are in liters. So this is 8.35 into 1 minus 3 moles. You can make a check. Now in the second one, what is the volume of an incandescent light bulb that contains this at a pressure? So here we know the temperature, we know the mass, we know the and also the pressure. So for what we have to do is, we know that N is equal to G upon M, so we'll replace this N, G by M, and then we will put the given weight into the value of R, and R, this pressure is in atmosphere, so we'll use this first one, because 0.0825, and then temperature always has to be in Kelvin, and we will put the pressure as it is. Okay, and this is the the molecular weight of the krypton, 83.80. So this yield 0.255 liters of the krypton. Okay, now similarly here, what is the density? In this case, we know that the density is equal to mass per unit volume, so we will replace here, and similarly we can find out density. Now we will jump on to the next problem. So this next type of problem is, this is combined gas law equation derivation. So we know that PV is equal to nRT, and PV upon NT is equal to R. So suppose here PV is constant, sorry, PV is and N and T are constant. So in this case, PV P1 V1 is equal to N1 RT1. Okay, sorry, we are PV upon NT is equal to R, so we are saying that P1 V1 is equal to nRT1. So R we are taking as a constant here, not PV constant. So this one is equal to R, and then we would say that P2 V2 is equal to N2 RT2. So it implicates that P2 V2 upon N2 T2 is equal to R. Now we can, from the, because this is constant, so we can write this form here. Now combined gas problem, again the tip is, you have to ask the new pressure, the temperature, moles or volume of gas. Okay, initial and final. The tip is that only one gas is mentioned, so there is no chemical and there are changing properties. Now seconds, in this step 1 we have to assign the variable, that is P, T, N and V. Okay, and use these superscript 1 and 2 as we saw in this equation, and then write out the combined gas law equation and eliminate the variables for any constant properties. Now the step 3, we will rearrange the equations to isolate the unknown as we saw in the first step, plug in the values and plug in means you have to put the values, make any necessary unit conversions and calculate units, calculate your answer and report it with the correct units and significant figures. Now, for example, we have a problem here. So it is given that a helium weather balloon is filled with Monterey, California on a day when the atmospheric pressure is 102 kilopascals and the temperature is 18 degrees C. Its volume under this condition is first condition. Upon being released, so now the temperature dropped and the volume has increased, assuming that the internal pressure of the balloon equals the atmospheric pressure. So what is the pressure at this altitude? So for this kind of problem, okay, what we will do, P1 we know that and P2 is unknown. So T1 we know that it has also always to be reported in the kelvins, and T2 is, since it is minus, so it is, you can see, and then V1 V2 already it is given. So here we have to find the P2 and we know that here R is constant, so we would use this relationship, okay, and N1 and N2, since the gases are same, so N1 and N2 has been cancelled, so we'll say that P1 V1 upon T1 is equal to P2 V2 upon T2. So here P2 is unknown, so what we will do, we will substitute all the values given, and then after substituting values, the value that is arrived is 32 kilopascals. So this was all about the different kind of ideal gas problems. Thanks for watching. Don't forget to like and subscribe.